Hello everyone, welcome back to Advent of Code. We're going to do day 9 today, but before we do that, I wanted to look back at day 7 for a minute. I was discussing Advent of Code with some colleagues this afternoon, and was reminded of a technique that would have been helpful on day 7, and which I've used on previous years, but just did not occur to me to use at all here. For not terribly interesting reasons, I guess. Remember day 7 was the one where we did that doesn't wait. Day 8 part 2? Oh, I see. If we looked at, I don't know. Let's say we checked out this, right? Remember, that was the one where we did luggage, right? Luggage contained in stuff. And we used state to memoize the traversal of the tree graph. I mean, I don't know. We made each one into a tree, kind of. Yeah, the data given to us was a graph, but we looked at it as two separate trees. One kind of like both of them had Goldbag as the root, but we looked at it once like following the edges in one direction and making a tree there, and the other time following the edges in another direction, making that tree. And so we used state to memoize the sub computations. Now, first of all, it turns out you didn't actually have to do that today, this year. I did it because I was thinking of 2015, I'm sorry, day 7, when we were, the first time we were ever given actually, was it a tree that we were working on this year? It's not, right? Because, yeah, it's not a tree. It's a directed acyclic graph, but it's not a tree. Anyway, when we were given a directed acyclic graph to traverse in 2019, day 7, it was a tree that was not very wide, but was very deep. Again, not a tree, but a directed acyclic graph. And there's a lot of common sub-expression sharing. So you would compute the value for some node many times while evaluating the root. It was an expression language we were parsing. I don't remember exactly why it was you ended up, but you can look at some visualizations of it, and it just falls off the edge of the page. It's super wide, well, deep. And so I figured this was a day 7 also, and it was a similar kind of problem. It would probably also discourage you from using a dumb traversal. And it was in fact too slow in 2015 to do the traversal naively, recomputing everything every time. So I used state in that in 2015, and I used it here. And it's fine, it works. But there's actually a technique that you can use in Haskell it's almost unique to Haskell. Much of what we're doing here is it exists in other functional languages, right? Yeah. I mean, even non-functional modern languages have stuff like map and lambdas these days. They didn't used to, but now they do. And type classes are kind of unique to Haskell, but not really. They're just simplified. They just make it simpler to pass dictionaries around. What is unique to Haskell is tying the knot, so let's look now at, hang on, do I have a change there? Okay. So what I did, is this actually going to work? Yeah, it is. Cool. I guess I could have just said diff with tilde. So you don't actually need state to do memoization if you're making a map keyed by some function where the value for a node depends on the values for other nodes. What you can do, as I said, is called tying the knot. So notice we had reachable from. I realize that's kind of a dumb name. I called it can reach. And that let me call, I don't know, I guess reachable from a root is okay as a name. But can reach of a goal. So this is, notice that the function has the same type, but it's much, much simpler. And importantly, it does not internally use any state, which is sort of nice, right? So the idea here is, okay, it's a very long set of function compositions, but we kind of have, we want to build a lookup table for, given a color, what is the set of nodes reachable from that color? And I'll include itself because that's convenient to do. And so we define this table to be a map built from a list where that list is, for each color edges pair in the original graph, we compute this function. Now, like, I don't know. I feel like this is a dumb, like, there's some surface syntax about what I've written that's kind of quirky and that, like, I think most Haskell programmers would say looks kind of dumb and bad. Like a do that just has like a single bind and then a call to pure, like really could just be a list comprehension, right? But I always get confused when I write those, so I don't do it. And also this really can just be an fmap. And I tried rewriting it with fmap and it was just too confusing, so I gave up. But okay, anyway, we write do. So for each color and edge list of edges in the graph that we're working with, we produce a map for our new table, or an entry in our new table, where the key is the color, and the value is insert the color after combining with union all of the table's entries for the color of each such edge. So edge color is a function that looks up the color of an edge defined here. So basically, if we read it in the other direction, we can say, over edges, we are going to map, looking up in the table, that edge's color, each edge's color. We'll union together the results, and then we will insert the current color. And so for bags which can not contain any other edges, it's clear that this works. You map this function over edges, and it doesn't even matter what the function is because edges is empty, and then you insert the color, and you say, from this bag, I can only get to this bag. For bags which have another color, have one or more other bags nested within them, it seems more confusing, like that this should work. It's like, yes, this would work if the table were complete, but we're not doing any ordering here. We're not like making sure to insert leaves and then insert things that depend on leaves. We're just inserting them all with from list and looking stuff up as if it were there. So does it work? And if so, why? The answer is yes, it does work. We'll talk about this line in a minute. It's not related to the interesting part. Yes, it does work. And the reason is because of Haskell's laziness. I did have to, though, switch from using data map strict to data map lazy because it because I actually need the laziness of the map here. We insert into when you call insert on a map, or in this case from list calls insert multiple times for you, on a lazy map, well, if you were to like implement your own map and do so without like thinking very hard about it, you would wind up with a lazy map because everything's lazy in Haskell by default. The strict map is just like the lazy map with an extra layer on top of it that makes sure to force items when you put them in for performance reasons, I think. But when you insert an item, you're like any value in Haskell is a thunk at first. It's until the runtime can prove that you actually need the value that in question. It doesn't actually compute the value. It just saves a thunk, a zero argument function in the runtime saying, if you need this, here's how to get it. And so we insert into the map a bunch of these, quote values, but we don't force any of them yet, right? And so each value in the map is a thunk saying, if you need to get me, then map this function over the edges. And again, for bags which have no contents, we don't end up needing to look in the map at all, so that's fine. For things that do have contents, when you force the thunk, it'll say, I got to look in the table at this other entry, and you get the thunk there, and you evaluate it. And if that was a leaf, then you get it. If it wasn't a leaf, then you map more functions over it, and you force those thunks. And so the runtime actually kind of does a topological traversal of the map when you look up your goal. It says, let me look up all its dependencies, look up all their dependencies, and so on. And you get that kind of for free just because representing graphs of interdependent values is the main thing the Haskell runtime does. And so if you can offload that work to the runtime instead of doing it yourself with state, it's much nicer. And then we have this little post-processing step. We build the table, and then we look up in the table. We look at all entries in the table and keep only those where the goal is a member of the set colors you can reach. And then... oh yeah, why was I making a set of colors? Actually, I guess I could have simplified this, huh? I don't actually need the set, because all I'm doing with the result is calling length. I was returning the actual set because originally I deleted gold in part 1. But once I moved deleting gold into can reach, part 1, we don't actually need to build from the set. I guess we want to because we need to make it unique. No, because there's only... yeah, this could have been simpler. There's no duplicates since we're working with the keys of a map to start with. So we could have just thrown all of this away and said length -1, basically. That would be a bit simpler. And then you can do the same thing for finding the weight, and it's actually even easier. Instead of looking up the weights in the map statefully and writing when we compute the right value, again, we build a table of all of the values at once, lazily, and then look up the ones that we need. And we don't end up needing any state at all. And so this is cool, and this works. I ran it. Oh, apparently I'm... okay, whatever. There were other changes here. But this is what I wanted to look at. And so one thing might leap out to you in comparing can reach... oops. Where am I? I'm lost. Okay. In comparing... wait, what? Do I even have the right thing checked out? Yeah, there's can... I don't know what the heck was going on a minute ago that had this giant function on the screen somehow. Anyway, so can reach and weight of, they both have this thing, right? Where they call m.fromList to build a table, and they iterate over the associations in G, and they call pure of color, and then some function on... they map a function over edges and then call some other function on the result of that map, basically, right? And so I thought it would be kind of neat to instead abstract that out to this... I call it fix because we're kind of implementing the fix function generalized to maps, where you give it a function in a map, and it gives you back a map from, or function in a graph, it gives you back a map to whatever kinds of values you were computing. And it's kind of interesting, but I don't think it actually turned out well. I think this is actually worse. Can reach and weight of are indeed a bit shorter. Weight of is very nicely short. But fixed map is just like a little bit too flexible, because what can reach and weight of want to do are both quite different. I think. Right? Like, can reach only cares about the color of the edges and the color of the current node, and doesn't care at all about the weights. Whereas weight of only cares about the weights of the other nodes. It doesn't. Oh, it cares about the weights and right. So in fixed map, there's a value you're computing, which in the case of can reach is a set of color, and in the set of weight of is an int. Both of them care about the computed values for all of their neighbor or their edges, of course. But fixed map cares about the color of the node you're can reach cares about the color of the node you're computing the value from, so it can insert that color. And doesn't care about, this is why it calls second, doesn't care about the numbers in the edges. Weight of is the opposite. It cares, because we're using uncurry times, this is now a function that takes both parts of a tuple and multiplies them together. It cares about both things in the tuple that's being computed, but doesn't care about the color of the edge that you're computing. So they kind of both have to do some gymnastics to ignore the parts of the data that the other does care about. And fixed map ends up being kind of awkward to use for that reason. So I think I will probably revert this change, but I wanted to show it to you guys. The last thing to note is that this fixed map, it feels very much to me like we're kind of implementing a catamorphism by hand for maps. And I'm sure there's something clever you can do with recursion schemes to get it to do that catamorphism for you, but I was not really up to trying to figure it out. So instead, I'm just going to I can create a branch or a tag or something that has the current commit on where weight of is extracted. Let's just revert it. That way it's still in the history. But in case I end up wanting it for some other reason, for reference, for computing some other map fold, for example, but it won't be in the final. It ended up being too general and clunky. Okay, so all that done, let's go look at day 9 now. And also, I noticed there's a gap here and a super large gap between here and 10. This is getting way. I guess this is because we're traveling much further in this step. We're flying a very far distance. Oh, I see. Yeah, this was the airport. This was the local airport, and this is the hub. And this was right on takeoff. I don't remember exactly when all these things happened. Anyway, it doesn't matter. Day 9, encoding error. With your neighbor happily enjoying their video game, you turn your attention to an open data port on the little screen in the seat in front of you. Though the port is non-standard, you manage to connect it to your computer through the clever use of several paperclips. Upon connection, the port outputs a series of numbers. The data appears to be encrypted with the Exchange Masking Addition System, XMAS, which conveniently for you is an old cipher with an important weakness. Okay, I don't know why we're suddenly excited to crack this code, but fine. XMAS starts by transmitting a preamble of 25 numbers. After that, each number you receive should be the sum of any 2 of the 25 immediately previous numbers. The two numbers will have different values, and there might be more than one such pair. For example, suppose you got the numbers 1 through 25 in a random order. To be valid, then it must be a sum of two of these numbers. Yes. 26 would be 1 plus 25. Yes. 20. Okay. Two different numbers. Yes. So it can't be 50, and it can't be 2. Oh, it could be... No, it couldn't be 2, because it's... you can't just have a single 2, and you can't have two 1s. Okay. But any number between 3 and 49 are valid, I guess? Oh, wait a minute. Ah, it's not... Okay. The preamble is not something that remains in force for the entire message. It's just after the preamble, any two of the 25 immediately previous numbers. Okay, I missed that. Not the 25 numbers from the preamble. Got it. So now, the first number was 20. Oh yeah, because they're saying we got them in a random order. So if the first number was 20, then we have all the numbers from 1 through 19, and 29 through 25, and 45. Got it. And we have to find two numbers that sum to that. Okay, that's interesting. So we're being asked to find how many... find the first number that breaks the property we've been given, that can't be expressed as a sum of exactly two distinct numbers from the previous 25. Now, wait a minute. Is it possible to have... Like, if the previous numbers were... If the first 25 numbers were all 1s, for example, could 2 be the next number? Can we use two different ones once each, or is it illegal to use the same number twice, even if it was given to you twice in the last 25 numbers? The two numbers will have different values. Okay, so yes, so you if you ever had 25 1s in a row, you could never get any more messages because no number would be valid. Okay. So there's obviously like an n-squared approach where you just keep a sliding window that's a list of the last 25 numbers. And each time you get a number, you look through all pairs of 2, throwing away any that are equal. So then you are spending, what is 25 times 25? It's like, yeah, 625. So you're doing 625 comparisons for each number to see if it's valid. A computer could probably handle that. I mean, I guess it depends on how large our input is, but it's probably not that large. But let's have a look. And just confirm that. Yeah. 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 Just kill it. Kill everything. What the hell? Yes, kill all associated buffers. I'm just like... Kill this. Oh my god. Get out of here. Okay. Let's just go to day 9 and look at our input. It's 1,000 lines. So 600,000 additions / comparisons is like, it would work. It does seem a bit gross though. It would be much nicer to instead keep like a multi-map, basically, where we keep track of how many times each number has occurred, but have it indexed, which I guess would be basically just an int map of ints. Yeah. And then when we get a new number, we can iterate over all the keys in the map currently and subtract the value in the map from the value we're trying to find, and see whether that is present in the map. Now these numbers should get larger as you go, right? Yeah. Okay, and just out of curiosity, how big is this? Million, billion, trillion. Okay, so it fits in 64 bits, but not 32, for what that's worth. Not that it matters. In Haskell, if we want it, we have easy access to arbitrarily large ints. But okay, we can use a 64-bit int, and it'll be fine. Oops. So let's just, well, actually, let me Haskell int map. Let me just look up. Hello? There we go. What I wanted to, oh, okay, it re-exports a bunch of stuff from data int map lazy. And what I wanted to look up is how to okay, it gives you all these functions you're not supposed to use. Okay. We only get data int map lazy. What I wanted to look at was the update functions. I think what I want is one that lets you update. Yes, here we go. So that we don't, like, let's say we put a 5 in the map, and then after a while, we remove the 5. I don't want to have a 0 be in there saying, oh, 5's there 0 times, because then the map just grows arbitrarily large and we have issues. So I want to remove it, and update lets you specify, yes, it should still be here. It should, and this should be its new value. Huh. Or say, no, it shouldn't be here anymore, and that's fine. So that's what we want. The other thing I'm thinking about is how exactly do you implement like a sliding window in Haskell? I think the best choice is probably data.sequence, because, or like, actually, I guess what we're looking for is a queue. Right? Because I want the queue to always have size 25. Okay, is there a queue in Haskell? So you can use data sequence as a queue, I'm aware. Oh, and there's a fancy toList implementation. I'm not going to do that by hand. Okay. Okay, so data.sequence is part of the standard library? I don't agree with that. Okay. What? Sorry, Google is playing me some weird fucking music that's like related to what I was listening to. Okay, here we go. Back to real life. Where's my link to data sequence? They're not going to give me one. I'm going to have to open up a search engine. Okay. Okay, so a sequence, and does it tell me here? Okay, there's nothing here about queues. You just have to. Wait, I had no idea. Louis Wasserman was involved in making data sequence? I know that guy. I mean, I also know of David Fewer. I don't know how to pronounce his name. I knew Louis was like interested in Haskell, but I didn't know he'd actually like worked on one of these foundational libraries. Huh. Anyway, so yeah, I mean, the data sequence, I guess, is fine for a queue. You just put 25 things in it, and then there's some way to like. There's view L, which I guess is fine, but there's probably something smarter, right? Sublists, well, not really. All right, how do you remove stuff? I guess, well, I don't need to remove stuff, do I? Because the view gives me that. And to construct, I have like insert left or insert right, I assume. Okay, we get. Oh, I don't need a view of the left because I can just use this, right? They give me this pattern synonym. Okay. But how do you add? Okay, add to the left and add to the right. Got it. Okay. So we're gonna need a few types here for sure. Import data sequence int map. Actually, how do they spell it here? First of all, it's data int map lazy, although we want a strict one, right? Okay. Do we want a strict one? Is it telling me I shouldn't have one, or data int map? Oh, data int map strict and data int map lazy are all different. I have no idea which one I want. I don't need lazy. Okay, so what's the deal with strict? It's careful to force values before installing them in the int map. I mean, that seems good. Warning. Int map type is shared between lazy and strict modules. Same map can be used. Yeah, okay. Oh, interesting. Functor, traversable, and data can actually contain non-strict values. Interesting. Well, it doesn't matter to me. I don't know. Let's just. I'll just add the stuff that I actually need from Seek. No, I don't know. And I'll probably add some stuff to the, like some operators maybe to the unqualified imports up here. Like I assume I'll want some patterns and, you know, insert right or something. But I can add that stuff later. And what is the pattern synonym again? Okay, that makes sense, of course. It has to start with a colon because that's the only legal, sorry, it's this. Has to start with a colon. Because that's the only valid operator name. Data constructors in Haskell, i.e. things you can pattern match on, must start with capital letters. But what about operators, where you name something, you want like an infix operator in the same way you can define an infix function? The only capital symbol is colon, so they all start with colon. This is just kind of declared to be capital, so this is how you can delta constructor and not an arbitrary function. Anyway, it makes sense that it's a colon followed by like the operator you would use to build something. Makes sense. Okay, so I want to check actually that I can use this thing. No, this one. In module data sequence. Tell me more. Ah, it's a constructor of this type, so it has to go here. Got it. It's not just a freestanding function. Okay, now we just get a bunch of warnings, which is fine. I'm aware I'm not using them. So let's let s equal s dot from list of 1, 2, 3. We look at s and it says, okay, it's from list of 1, 2, 3. And then what if I say let x, no, let x more equal s? X is 1. Okay, yes. So you probably have to turn on a language feature to define pattern synonyms, but I guess if you import a pattern synonym, there's no language feature needed because it's just a pattern like any other. Okay, just wanted to check that. Because sequence is not actually built out of this constructor. It just exports this as a pattern to you that you can use to pretend it looks like that. Internally, it's a much more complicated data structure. So I really don't know what I'm going to want, like what types I will want to share between part 1 and part 2, or even what, like, forget about types. I guess, okay, first of all, our input is actually a list of int. And it's just map read lines. That's simple enough. So let's just write everything in part 1, and then I can figure out what I might need to extract out to be shared. I don't know. Actually, like, we'll probably need like a state of the protocol state or something, which is the 25 most recently seen things and the order that they should be dropped in. So let's define a type for that. Data, it's not really, like, state isn't exactly right, but I guess I'll do it. So the state is a state of, first, an int map of ints, which is basically just a bag, a multi-map, and also a seek of int. Yes. And I think that actually our input should be a state and a list of int. So that the prepare function rather can do the work of building up the preamble for both part 1 and part 2, which I assume will only care about the preamble insofar as it makes the rest of the task simpler. It will be nice to maintain the invariant that in part 1 and part 2 we always have a preamble of 25 items. So let's do this. Let nums equal this, and then preamble text equals split at 25 nums. Is split at, I always forget if it's in data list or the core, but we'll find out. I guess there's some things we'll need for like updating a state object with a number, right? Yes, that will be a useful function. Data, or not data, consume number takes an int and gives you back a function from state to state. Now we might not be able to use this in prepare because we actually don't want to drop things while we're going, but yeah, I think we won't. So let's just leave it undefined for now. But I'm sure part 1 and part 2 will both want it. Next, we let what are we calling these things? We'll let the bag, I guess, be... Does it map have from list with or something? You would think, yeah. From list with? Yeah, it does, okay. M.from list with plus of x1 for x in preamble. That's fine. You could write this with a zip of repeat 1, I guess. That's probably better. Zip. Well, actually, it's kind of in the wrong order, isn't it? Yeah, let's just leave it like this. So that's our starting int map. And our Q is S from list of preamble, and that's it, right? In now we're building a pair of, we said it would be a state and then the remainder of stuff to process, and the state takes the int map first. Okay, so state bag q text. Okay, that looks good. Now something to think about is, what order does from list build in? I assume it puts the first items on the left. It doesn't actually say. But it kind of has to, doesn't it? I don't know. Yeah, all right. We don't need to read, like... I mean, we can just find out. We already know. We already did that. We already did find out. It's right here. We built it with from list, and we got 1, 2, 3, and unsurprisingly, when we said what's the leftmost element, it was 1 and not 3. Okay, that's what I wanted. Because we're going to, in the future, be adding stuff to the end of the list with this operator, and then removing it from the front of the list with this. I guess I, in principle, should maybe import empty, but I don't expect to ever run out, so I won't. Okay, so here's the thing to do is, well, maybe before we work on consume number, we can say number allowed, valid. What do they call it in? They call it valid. All right. Valid is a function from. I don't know. I guess we'll take the state argument first. I'm not sure. State in pool. Valid of state m. No, I don't care about the q. X equals how do I look something up in a map in a way that lets me react if it's not there? I guess lookup is the thing to do. I don't really want find with default. Yeah, you look up the current value. Okay, we'll look up one value and be in maybe here. So maybe false of something. Maybe false of pair m dot lookup m. Lookup takes its arguments in the other order, huh? Where pair of x equals m dot member what exactly am I looking for here? Oh, no, this is not, this is more, okay. I'm writing the wrong function. I need to look at each entry currently in the map. And then for each such one, see if it has a matching pair. Okay. Any let's just put x back in scope here. Maybe false. Yeah, I kind of do still want that, don't I? Has pair of No, this is still wrong. I don't need to look up the current entry at all. I need to any pairs with X. Well, X is in scope. I can just say any has pair of m dot keys X M, where has pair is a function from int to bool, and has pair of y equals m dot member we have X, we need it to be composed of Y plus something, so it should be X minus Y. Yes, okay, that was simple enough. It didn't need it, okay. It didn't need me to do anything weird, and it wasn't complicated enough to need an internal type. I just kept getting confused about what I needed to do. All right, and now we need a way to update the state when we get a new number, which should be simple enough. Consume number of X state MQ equals state of M prime Q prime. Easy. Where M prime, oh, I can actually just destructure the Q here. Oldest others we'll call it Q prime anyway. Where, and let's do Q prime first because it should be easy. Q prime equals, what order do you get the arguments? Okay, I see. It puts the sequence kind of where the pipe is in the operator. So we want to put our thing on the right, therefore we write others X, right? Yes, that type checks. And M prime is M dot insert, no, insert with plus type of insert, takes the key first, X and 1 and M. What are you mad about oldest for? Ah, yes. Because I need to do more. I need to also remove the oldest from the map. M dot update decrease, I guess we'll just call it, of X, which is our key, and finally decrease of 0 equals nothing, decrease of n equals just the predecessor of n. How's that look? Not X, but oldest. Thank you, HLint, for warning me that this is unused. What are you upset about here? Pattern match is non-exhaustive. I agree, but I don't care. I don't expect the queue to ever get empty because I start with it having 25 things, and I always add one whenever I remove one. So now we're ready to write part 1, I think. Part 1 of state message equals I guess we want to iterate, no, not iterate, fold R, probably. Fold L? Yeah, fold L, I guess, since we have a starting state and we want to run that against the first item in the list. That kind of stinks, because fold L is not lazy. Huh. Well, okay, I guess I'll just write it myself. I'm sure there's something smarter I could do here, but I don't know what it is. We obviously need some recursion here. I'm just trying to work out whether we need an internal helper function used by part 1 or whether like part 1 itself should just be recursive. I think part 1 itself can be recursive and it's like totally fine. And that seems the simplest way to do it. Yeah, so that's actually kind of cool. So instead of taking a message, we'll take x's. And we'll also say part 1 of anything and the empty list equals error, whole message valid, where valid of state x equals part 1 of consume number x state and x's. There you go. And otherwise equals x, the first invalid number. What are you mad about here? Redundant bracket. Oh yeah, I mean, but I feel a lot more comfortable when I destructure lists inside parentheses. Okay, let's see if this works. I mean, it might. It's a large number, but it didn't break. And I assume if we look into our input, we will see that that number does appear eventually, so it didn't just come out of nowhere. All right, it seems like a reasonable guess. Let's give it a try. That's the right answer. Cool. So let's day 9 part 1. Let's get that committed. And back to the puzzle. What's part 2? The final step in breaking the encryption relies on the invalid number you just found. You must find a contiguous set of at least 2 numbers in your list which sum to the invalid number from step 1. Okay, so this is interesting, but not actually that hard. Because what exactly, is there really some efficient thing here involving like walking in from both ends of the message? You could like which sum to exactly the invalid number, which is not a sum of any 2 numbers before it. But they might include numbers after it in principle. The set doesn't. The message doesn't have to grow larger. All at once. You could have like. It could be kind of spiky. So in principle, our number could be the sum of two numbers after it, or one number before and one number after. So what the obvious inefficient thing to do is to just like iterate through all pairs, not of numbers in the list, but positions in the list, which again there will be like actually kind of a lot of now that I think of it. There won't be 25 squared like there were before. We're now working with a very large number, which is the square of the number of items in our input, which is 1,000. So there are a million ways to choose pairs of numbers from this list, or sets of numbers from this list. Well, 500,000, because before after is the same as after before. Okay. Still kind of a lot. And worse, the cost of computing the sum of such a number is also linear? Right? To add up the first like 50 of these items takes 50 50 additions, and the first 100 takes 100 additions, and so on. So there's actually something like n over 2 work to do in each of our n squared over 2 sets if we did things the absolute dumbest way, which is like n cubed, so it's like a billion things, a billion additions if we did it the totally naive way. It seems kind of expensive, right? Maybe the computer could handle it, but also it would be kind of rewarding to figure out something clever, wouldn't it? I often do my admin to code fairly brute force, and I don't mind that. But I know in like day one, I did it brute force, and everyone was talking about like the efficient way to do it, and I was like, oh, I didn't even think about doing it efficiently, and I felt kind of silly. But at least the algorithm that you would do was pretty easy once someone just told me, oh, you maintain 2 pointers. Okay, great. Yeah, that makes sense. So here, it seems like you kind of want to maintain 2 pointers, like, but not from the beginning and the end. Because, like, suppose at some point that I was considering this set of numbers, and I found it was too small. I could either add one to the end, or I could add one to the beginning. And both would make the set larger. And you could say, well, okay, but if you add one to the beginning, you've probably already considered this sum before. But I'm not sure that's true. Like, if the previous one we looked at was this, I don't know. Huh. Okay, so something we could try instead of like adding sequences of numbers. Okay, first thing I guess is we could try sorting the list. Is that useful? It was useful before. Although actually, isn't this the subset sum problem, like known to be hard? Right? Am I crazy? Subset sum problem. It's a decision problem. There are several efficient equivalent formulations. Given a multi-set of integers, is there a non-empty subset whose sum is 0? Now, that's not quite what we have, but we can map our thing to that quite easily by adding... Oh no, I guess it's not quite, is it? Well, isn't its sum being 0 is the same difficulty as its sum being some other number, right? Huh. I just want to make sure I'm like not missing something about our problem that would make it not have this NP hard issue. Of course, this says it's a decision problem, and we're doing something more difficult. We actually want to find the numbers, but I don't expect it to be much more difficult in practice. I mean, we're not asking if they sum to 0, but I don't see how that's conceptually any harder than them summing to any particular other number. So there's this dynamic programming solution which seems reasonable. Sorted in increasing order, yes. Define a Boolean valued function to be... There's a non-empty subset that sums to S. Sure. The negative values and the positive values. Huh. This actually does seem to care about... Maybe negative numbers actually do make it substantially harder. And the fact that we have positive numbers adding up to something other than 0 makes the problem easier. Okay, well, let's think some more about the problem then. It seems like sorting the list would be useful as a start. Oh, right, it has to be a contiguous subset, right? It does, doesn't it? In the problem spec. Contiguous set of at least 2 numbers. Yeah. So this isn't that hard. We do just need to maintain 2 pointers into the set, into the queue, the sequence, and as long as we sorted it, we start with, let's say, this as our window, and if they add up to too small a number, we increase the range we're looking at, and if they add up to too large number. Okay, let's say we're looking at these 3 already. If these are too small, then we say, all right, now I'm looking at these 4. We add 1. And if they were too large, we say, oh, well, let's look just at these 2. And so every time we get, we sort of inch along, expanding and contracting until we find something of the right size. And we just need to maintain, so that we avoid doing a bunch of sums in between, we also maintain the sum that we currently have and just add or subtract a single number from it. All right, so it looks like all the stuff that I thought might be shared between the two is actually not shared at all. I don't even need to split it into the preamble. Do I? In your list, not the stuff after the preamble. Okay. So in fact... We don't need a state machine. We don't need like friggin' anything. But okay, part 1 expects an input. I as state mq and text is let we'll just call part 1 again here. It's a little wasteful because we already called it in main, but not terribly expensive. Let goal equal part 1 of I. And then we have to do like actual programming. Well, not yet. We need to build a queue. So we can say queue equals, how do you add like a large number of things into a sequence? Is that even what I want to do? We could concatenate 2 sequences, which I guess is fine. Yeah. I knew that was an option, although I didn't know what the operator was called. So now what we want is I need to sort the list anyway, right? And there's nothing. Oh, there's even sort for sequences? Why? Okay, apparently there is. Q is sort of preamble concatenated with S from list of text. Okay. And now we need, like in search Q01 is the idea. We're going to write a function called search that takes, no, I don't even, actually we could search for 0, 0. Okay, so question, like, oh. What do I want to be the invariance of search? Like, what do I want the 2 indexes to represent? I guess the index at 0 is, I want them both to be inclusive, kind of, right? And I also want them to always be different. So really we should search with 0, 1. And then the sum of S take 2Q. So this is the only time we're actually going to sum things. Right. So where search of low high S equals when S is equal to, actually it should be equal case compare S to goal of, if it's equal, we should return, what are we meant to return? The sum of the smallest and largest numbers. So S dot, how do you look something up unsafely? And it takes the, oh, look up, I was looking at the wrong indexing. Here we go. I was looking at the data int map. So, but yeah, we want index here. Fine. S index of Q low plus S index q high, we could actually, let's actually just move this let in stuff into our where so that we have access to it. Where. Okay. What are you mad about search? Oh, it returns an int. Okay. But this is actually index of q low, index of q high. We're adding them together with plus. There's actually some duplication here, which in most languages you would not bother to factor out. And in Haskell, I think a lot of people still wouldn't bother. But I kind of like to notice that this is a general case of a specific case of a more general problem. I don't know. Like, is this really better? Add together the low and high elements indexing on Q, and we need to import that. I like it, but what's wrong with this? S-index is applied to 3 arguments. Have I forgotten how on works? It won't tell me because my function doesn't my program doesn't compile. Data function. Oh my god, what is wrong with this doc? That's like, it's got the styles all wrong. Anyway, it takes 2 A's and an A to B. This looks right. On the result of applying unary function u, so we have our unary function is s.index of q. Our binary function is plus. We have low and high, which are, this looks right actually. Huh. Is there something wrong elsewhere, maybe? Search is applied to too few arguments. Ah, there we go. So it was inferring the wrong type for search because no? All right, let's give search a type. Int. Oh, no, that's right. Int, right? That's what I want it to be. So this was correct. On is applied to too few arguments. Looks right to me. Oh! I always forget how operators work when you define them as like infix operators of textual functions. If I'd written something like this, it would be very obvious to me that we're adding together 2 things, what's here and what's here. But at some point when I was learning Haskell, this misconception got into my head, and even though I know it's not true, I just like can't shake it, which is that inserting, I imagine, even though, again, this is wrong, x, f, y, z, I imagine this to be calling f, x, y, z, but it's not. It calls f of x and y of z. Okay. So really, if you wanted to do this, you could say on like that, and then it's fine. You know, is this really better than what was here before? No, it's not. So we're not going to do this. I just wanted to point out, like, it's kind of cool, right? If the functions or values we were using were more complicated, it would be reasonable, but here it's not really. Like so. And if it's less than, it's too small, then we want to call search again. And the low should be left the same, high should be increased, and the sum should be s plus s index high prime, where high prime equals high. And if we get something that's... Why are you mad about this? Oh, I didn't pass a Q in. Okay, and finally, if it's greater, we search low prime high s minus s index of q low prime. No, the original low. Because we're subtracting one we've already seen, where low prime equals pred low. No. We're increasing low to see one fewer thing. Now here, in this case, low prime is only used once, so I could just inline it, but I like the symmetry. Redundant bracket here, I guess. Sure. So this compiles, and you're right, we don't care about the map. Is it correct? I guess we'll find out. All right. I mean, it's a number. It's not the right answer. Too high. I guess. I mean... Is it like visibly obvious that it was too high? Yes. I added together two numbers. I added together a large range of numbers, just the ends of which equaled this, and I said, yeah, those add up to this. That's obviously wrong. Wait a minute. I sorted the list. That's not allowed. We care about the original input list order. Does the same algorithm work at all if the list isn't sorted? Like, we're looking at these. Well, okay, we're looking at, like, let's say this. I guess, like, we keep slurping up stuff here until we get to something that's larger than our input. And at that point, we drop the first item. If the result is still larger than our input, we keep dropping the first item. Yeah, I think I just need to do the exact same thing, but not sort. Except also, like, how did my program give me something obviously wrong? Even with a sorted list. I don't see how this was possible. Okay, well, let's like... It's a little hard to debug part 2, actually, because I made it depend on calling part 1, which means I have to, like... Okay, let's write a function that's like part 2, but that doesn't depend on part 1, and it just gets given a sum and a list. And then part 2 will call that. No. Range summing 2 takes a list of int, it takes probably an int first, right? And a list of int, and returns a list of int? I don't know. Sure. And we'll turn these into sequences soonish, but actually I have to take a quick break. I'll be right back. All right, I'm back. I just ran out of water, and like it takes a while to fill up the pitcher, so I didn't want to like leave that leave that pause on the recording. So right, should I be taking sequences or ints? Lists, rather. I guess I may as well take sequences because that's what I have anyway. Range summing 2 goal q equals go, well, search 0, 1 sum, like we're doing the same thing here, right? S take 2 q, and then we pull this whole search down here. But indented correctly. Oh my god. There's like a number of valid indentations and you can cycle through them, but like, okay, here we go. Now it returns the wrong thing because, sure. So what I want to do though is inspect the entire range so I can debug what is going on. So what I will do is, how do you, in a sequence, look up sub lists? I mean, I guess we have take and drop, don't we? Yeah, that's all I need. S take high minus low, S drop low Q. Okay. So let's try a simple example here. Oops, get out of here, Scratch. Range summing to 10 of S from list of 1, 5, 9. I guess I'm not doing this very well, am I? Let's add to 15, 5, well, that's a little bit, 18, 5, 9, 4, 1, 7, or something, I don't know, whatever. So this should give us the range 5, 9, 4. That adds to 18, right? But it doesn't. It just says 5 and 9. That suggests I'm managing my sum incorrectly. Okay, can we do something simpler? Like, first of all, this should really work, right? 5, 13. No. Okay, I just need to subtract 1 from my result or something. Or high minus low. Yes, because these are both inclusive. We should actually be adding 1, I think. $594. Okay. Well, that's kind of weird that this is working, actually, right? Because, well, okay, let's also try like putting a 3 here, and then we should get 1359. We do. But if this works, then what's wrong with the other thing? Because we haven't really made any changes here to the core algorithm, I don't think. Maybe I was summing the wrong item here. But I don't think so. Our low and high represent the lowest item we are including and the highest item we are including. They start at 0 and 1. And if we discover that S was less than our goal, then we add 1. I'm still not sure, by the way, that this entire algorithm is sound. Because we're not actually exploring all of the valid pairs, right? But I think it's still okay, because if we look at a set of, like, I don't know. Let's look at our input. Let's say we looked at you know, this sum, and we found that it's too large. Then we never need to consider any sums, any ranges, that include all of these numbers. Only ranges that drop some from the front or that drop some from the end. Well, that's not the right way to put it. Ranges that end before this one does, or begin after this one does, I guess is what we really need to consider. If we were looking at like all of these, I don't know. I guess like we slurp up a whole bunch of items until we finally find a sum that's too large. And at that point, the only thing we can do is release the first item and say we'll never include it in the sum. And I think that's correct to say we would never include it. Because with that number, it's too large. And we didn't run into the goal on the way here, right? So it's not possible that a sequence ending before 97 can sum to our goal. Because if it includes the first number, it's too large. Sorry. A sequence that ends at 97 and starts at the first one is obviously invalid. But could there be one that... could there be any sequence that includes our first number? No. We looked at all the ones that don't include 97, and all the ones that do include 97 are too large. So we can throw away the first one forever. Now, having done that, the question is, can we now throw away the second item if our result is still too large? I don't think we can. That's what my algorithm currently does. But that's not valid, because we can do a really simple example here by hand. I think. Let's say the sum we wanted was... Well, okay. It's less than 60. It is hard to construct counterexamples by hand, isn't it? Maybe there aren't any? Yeah, let's say we wanted 44. And these first 5 items were our entire list. Our current algorithm would say, okay, how about 10 and 17? No, that's too small. How about... Oh, no, this would work. It would still find 44. Because it would say, how about this? It's too small. And then it would say, how about this? Perfect. Why does... I know the, like, I don't know, maybe you guys are excited about the Google Music bizarre stuff that you can't hear. But like, I told it, play me some Weezer, which I recently remembered existed. And it did that for a while, and then it just starts diverting into like Indian music. I don't know why it thinks those two are related. I have to like stop it and say no. Like, play actually related music. We'll pick some band other than Weezer. So it is true that no sums including 10 could ever be right, so we can throw 10 away. But suppose we get to something that is, I don't know, like... Yeah, let's say we wanted this to be our sum, which is what, 47? Actually, this is still going to find the right answer. I'm trying to like construct a counterexample where I can say this is not correct. And what I think it needs is to have a small number in between two large numbers, so like this or something. 50 and 23. I don't know. This is too hard. I somehow think it is right, because we throw away the first item and we have a range. The problem is that we could shrink the range in two different ways. And either one of them could be valid, right? I think so. No. Well, when we first shrank the range, we got this far, right? The only valid way to shrink it is not like this, because we already looked at that, but like this. However, once we've shrunk this range, we could shrink it in either direction. We could say, let's try this pair. Oops. Or we could say, let's try this pair, right? Either of those is valid. We haven't looked at either set of those. That's the problem. It doesn't really explain why we got a completely impossible answer, but it does explain why the algorithm's not quite right. And I think this is one of those things where you want like a dynamic programming approach, where you have a table of the sum of a range. You keep track of like a sum of a range from two indices that you like keep those that memoized somehow. And then when you get something that's too large, you have to try both ends. Try dropping off both ends. Because, okay, this would only happen if let's say we got to here. If the number that we added was smaller than the number at the top, then of course you can't succeed by shrinking this one anymore, right? It'll still be too small. You would need to shrink this way. No, I'm like super confused. I could just do this the dumb way by hand and be done. Like, we would do a billion operations and that would take a while, but not forever. I think we should just do like the kind of thing I was saying about dynamic programming, where we keep basically a map from low and high to sum. And then do an n-squared search through all pairs of indices. Like, we don't even have to do an n-squared search, I don't think. Because if something is too large, we can just try... We can try decreasing... Yeah. If something is too large, then increasing the index... increasing the last index or decreasing the first one is the wrong idea. But even the n-squared search should be okay. It's only a million choices, right? So let's just try building that table, I guess. So I guess what we want then is, oh no, we're gonna need, okay, let's replace m dot with I dot and import this as I for int map. And we want a lazy map. And we want range sums takes a seek, I guess, event, produces a map from int and int to int. Range sums of Q equals do? No. M dot from list of do. Low from S length, like so, and high again, the same thing. When no, I need guard, right? Guard again. Guard, actually, that's stupid. Low up to that. There we go. Now we don't need any guards. And we will just say if low equals high. Actually, again, we can simplify that, right? Pure of Q dot index low. Oh, but we need actually a tuple here, right? Low Q dot index of low plus, well, it's the same as this, really, I think. We'll say and do. There we go. So basically, we need something to initialize ranges, to handle the base cases, and that's this step here. And then we say we need circular references here. That was the whole point. So we say where table equals okay, because I need to be able to look up in the table the range from low to high -1, basically. Well, this is fine. I can just say S index high plus table at low high -1. But I need to wrap this in pure and say it's the entry for low high. Q dot index, S dot index, there we go. Seek of A? Oh, I didn't give it a Q. Yes, and it doesn't like these brackets. I don't care, I'm keeping them. Why are you mad about this one? Oh, because it doesn't have ++2. So now if we said, let's go back to our example here. Range sums of this. We would get a sort of large list, right? It says for 0, 0, you get 1. For 0, 1, you get 4. For 0, 2, you get 9. This all makes sense. And if we look up, like, I don't know, 1, 4, we get 21. That's 3 plus 5 plus 9 plus 4. It's 14, 18, 21. Yes, this looks correct. Okay. So now we can do part 2 more simply. Well, yeah, I'm just going to look at every key value entry in that list and take the one I'm happy with. We'll make it be a list event in case there's multiple ways to do it. There shouldn't be. It'll be, just throw all this garbage away. Map uncurry no. All right, we have to actually build a couple. Oh, some of the stuff I threw away was not useless. I need the goal and the queue anyway. This is just what I don't need. Map of let's do a list comprehension. I'm bad at these, but why not? I don't know. I'm bad at them? Let's just do a do notation. It'll be easy. We'll do low, high, sum, total from range sums of Q. Guard that total equals goal, and then return S index Q low plus S index Q high. Import guard, sure. Oh, range sums gives us a map. Oh, all right, that type checks finally. So if I run this, will anything good happen to me? It should take a little while, but not too long, right? Yeah. There was one way to do it, and that's what it was. Wait, it's still too dang large. Is that the same wrong guess I made before? It is. Maybe I'm not understanding the problem. Oh. Well. Okay. Contiguous set of at least two numbers. Here's our example. All the numbers from 15 through 40. This is the same. Okay. That sum up to the invalid number. Are there negative numbers in my input? There aren't, right? No. I just... Contiguous set of numbers which sum to the invalid number. And my invalid number was this, which is 3, 6, 9, 10 digits starting with 1. 3, 6, 10 digits starting with 3. Like, it's just impossible that I could find a sequence of any number of numbers adding to this if two of them add to a large... No, sorry. Adding to this if any two of them add to a larger number. But I've done it twice, and it's been wrong both times. But, like, wrong in the same way, despite using two fairly different, I would say, approaches. So it must be just, like, there must be something I'm completely doing wrong. Oh, wait a minute. This is exactly twice that other number, isn't it? Yeah. So why is it? Oh. Well, I don't quite understand how that happened. I somehow produced the range. Okay, well let's fix part 2 at least. Let's just get rid of the type signature so I don't have to keep fixing it if I make changes. And I'm going to say low, high, and also this. So we're going to return the index pair and also what it sums to. And I suspect it'll be the same index twice. And I'm somehow counting that twice, and that shouldn't be allowed. Yeah. So number 643 to 643. But, like, why is that in the map? I mean, I guess it makes sense. Ah. Because I put it there, of course, is the obvious answer. But more generally, I said low and low sums to this number. And it does. Because I want my low and high to both be inclusive. But I don't want that to actually be a valid range. And also, like... how is my total... Oh, I sorted the list again. I didn't remove the sorting step. Oh, of course. I ran through the sorted input list and found two entries, two indices that met the criteria I wanted. And then I indexed into the original list, not the sorted list, to say what numbers are at those indices. Okay. So that ought to fix it, right? Except I'll still get... No, this time I got better numbers. It said there were two of them. Ah, yes. This one... I don't totally understand why I'm getting this. Oh, yeah, it's because I didn't tell the thing that it's illegal to have low equal high. And then it said, oh yes, the sum from low to high is including the number just once, which is correct. But then, when I handle it in part 2, I assume that those two are not the same because they're not allowed to be. So really what I should also do is guard that low not equal high. And this will get rid of the duplicate, or the excess answer, and give me the real one. Interesting. This is like very... This is still wrong, right? 3, 6... Ah, no, this is only 9 digits. So it's a smaller number than this one, which is 10 digits. Okay. I'm happy enough to try that. Now it's too low. Oh, right, because I noticed something last time I was reading the text, but I didn't actually do it. Which is that you're not supposed to add together the first and the last, but the smallest and the largest. Previously, when I was imagining that I should sort, I thought those were the same thing, and so I didn't think much about it. But okay, that's fine. We can say... let range equal s dot drop of low, and then s take of high minus low plus 1 q. And I will say pure of minimum range plus maximum range. So we got the two bounding numbers. What we wanted was the smallest and the largest. We're supposed to add them, right? Yeah. Here's another different number. It's exciting. All right. Okay, I made several mistakes today. I would not call today much of a success, honestly. But I think mostly it all came down to this sort that I put in and forgot to take out when I decided it was invalid. I wrote up this whole like range sums thing. But I still think, though, that the original approach was not correct. It would have not considered some valid ranges. And so this of like sharing work to build an index, it's a large and wasteful index. A lot of it would not be necessary. We could do better. Like, if we told range sums the goal we were trying to build. Well, let's commit this first. Oh, I'm not using on. Let's clean this up. Any other H-lint warnings I should get to? What's wrong with part 2? Nothing. Okay. Day 9, part 2. So what I wanted to look at, though, is I could make a bit less work for myself here. I think. Maybe not. I want to basically say if what's already in the table... Yeah. What I want to do is this. Take this value, let subsum equal this, right? Guard that subsum is less than goal. And only then do the recursion. What are you mad about here? Oh, subsum. Now you'll be mad about the types, which is, or mad about goal. Wait a minute. Honestly, it's... Oh, I don't want guard, do I? I want to, like, stop the previous iteration. I don't want to take every element. Okay. You could speed this up, but the video is already long, so I'm not going to do it tonight. But what you could do is generate a sublist of this, where you, for each item, could you? I don't know. It's a little bit hard. But somehow it should be possible to, once you get to a subsum, it's like M0 or something. Does guard do the same thing? It doesn't, right? Because it can't terminate. A guard here couldn't terminate this list anyway. We'll just throw that idea away. Okay, that was day 9. Thanks for watching, everyone, and I'll see you next time.